Every now and then in science, a single paper comes along that just changes, well, everything. Back in 2017, a team from Google published a paper with a pretty bold title, and it became the blueprint for almost all of modern AI. So today, we're going to break down that very paper. Attention is all you need, and the incredibly architecture it gave us, the transformer. This one sentence right here from the paper's abstract, this was a really big deal. At the time, all the best AI models were built on these super complex systems that processed information step by step. And this paper basically proposed throwing that entire playbook out the window and replacing it with just one single powerful idea: attention. So here's how we're going to tackle this. To really get the genius of the transformer, first we've got to understand the problem it solved, what we'll call the sequential bottleneck. Then we'll dive into its amazing solution, self-attention, and see how that gets built into the full model. And of course, we'll check out the incredible results and the massive legacy this paper has today. All right, so to really get why this was such a revolution, you have to understand what came before it. Before 2017, the absolute kings of language AI were these models called recurrent neural networks, or RNNs for short. For tough jobs like machine translation, they were the best thing we had. So these older models worked sequentially. Kind of like how you're reading this sentence right now, you process one word, then the next, and you carry the meaning forward. RNNs did the same thing. It seems intuitive, right? But, and this is a big but, this approach had a massive, fundamental flaw. And that brings us right to the heart of the problem. That whole one word at a time thing, the thing that seemed so logical, it was actually a giant bottleneck. It was holding everything back. This step-by-step process causes two massive headaches. First, you can't really speed it up. It isn't parallelizable. You can't process the 10th word in a sentence until you've already processed the first 9. That makes training them on modern hardware like GPUs super inefficient. The second problem? Memory. By the time an RNN gets to the end of a really long paragraph, it's kind of forgotten what was said at the beginning. This table from the paper just nails the point home. With the old models, the number of steps grows the longer the sentence gets. We call that O of n. But look at self-attention. It's O of 1. That means it takes the same amount of time, just one computational step, for any two words to talk to each other, no matter how far apart they are. This isn't just a small tweak, it's a complete game changer. So how did they pull this off? This brings us to the core idea of the whole paper, the magic ingredient that just shatters that sequential bottleneck. It's called self-attention, and it's a way for the model to look at the entire sentence all at once. Okay, so what is self-attention, really? Well, imagine for every single word in a sentence, the model asks, how important is every other word to understanding this word? Instead of information flowing in a straight line, it creates this web of connections where everything can look at everything else at the exact same time to figure out what it means. Now, the paper gets technical, calling it scaled dot product attention, but let's break it down into 3 simple ideas. First, for every word, we create 3 things: a query, a key, and a value. The query is like the word asking a question. The key is like a label on every other word saying what it's about. And the value is the actual substance of the word. Second, the query from one word matches itself against the key of every other word to get a score. And third, those scores are used to create a weighted blend of all the values. The result, our original word is now packed with context from the entire sentence. And here's a perfect example of why that's so incredibly powerful. Take a sentence like, the animal didn't cross the street because it was too tired. What's it? The animal, right? An older model might struggle with that, but with self-attention, the word it can instantly look at both animal and street, see that animal is a much better match for something that can be tired, and boom, problem solved. Okay, so we've got this amazing self-attention mechanism, but how do you build a whole model out of it? Well, the transformer isn't just one layer. It's a complete architecture designed to do some serious, heavy lifting, like translating languages. From a bird's eye view, the transformer has 2 main parts, an encoder and a decoder. The encoder's job is to read the sentence you give it and really understand it. The decoder's job is to then generate the new sentence, like the translation. The model in the paper stacks 6 encoder layers and 6 decoder layers. And the really wild part, it does all this with zero of that old school sequential processing. So the encoder takes in the whole sentence all at once. And as it passes up through those layers, each self-attention mechanism lets every word look around and get a better and better sense of its own meaning and context. By the time it gets to the top, the model has this incredibly rich, deep understanding of the original text. Then you've got the decoder. Its job is to actually write the translation. Now, it does this one word at a time. But here's the clever part. For each new word it writes, it first looks back at the words it's already written to make sure it makes sense. Then it uses another attention step to look over at the encoder's complete understanding of the original sentence. This lets it focus on the most relevant part of the input to predict the next word. But the authors didn't stop there. They figured, why have just one attention mechanism when you can have many? This is called multi-head attention. They used 8 heads. The best way to think about it is like having a committee of 8 different experts looking at the sentence. One expert might focus on grammar, another on meaning, another on what pronouns refer to. By getting all these perspectives at once, the model gets a much, much richer understanding.
Okay, so the architecture sounds amazing, right? But the real question is, did it actually work? Because a beautiful theory is one thing, but performance is everything. Well, the results came in, and they weren't just good. They were revolutionary. On a standard translation test, the big transformer model didn't just win, it smashed the previous record. It beat the best models out there by over 2 full blue points. Now, in the world of machine translation, an improvement like that from a single model was just unheard of.
The hard data tells the story. The transformer hit a 28.4, way ahead of the previous best, and did the same on another translation task. But maybe the most impressive part? This performance was achieved at a fraction of the training cost, so it was better, faster, and cheaper, the trifecta.
And that really brings us to the legacy of this work. See, this paper didn't just introduce a better translation model. It introduced a new, general-purpose way of thinking about sequences. And in doing so, it laid the foundation for the entire next era of AI.
Think about it. All the massive large language models that dominate the headlines today, they exist because of this paper. By getting rid of that one word at a time bottleneck, the transformer made it possible to scale models up to a size that was simply impossible before. It unlocked a new level of training. The authors knew they were onto something huge, even suggesting these ideas could be applied to images, audio, and video. And that leaves us with the big question that continues to drive the field today. This was a fundamental shift, moving from a linear, step-by-step process to a parallel, relational one. The transformer didn't just give us an answer, it gave us a whole new way to ask questions.